Hello class, this is Dr. Anderson and we are finishing up renal physiology, concentrating on renal pathophysiology. So when we talk about kidney and pathophysiology or kidney dysfunction, the kidneys are just so important to anesthesia and clinical practice. The kidneys are going to be clearing some anesthetic substances. What have we learned about clearance? That clearance is the mils per minute of plasma that is cleared of a particular substance. So if you have a particular drug and it has a lower clearance, that means it's going to be around longer. And that's something you take into consideration. And then of course drugs that are sedating or dealing with pain, so barbiturates and opioids, so morphine and fentanyl and all those sorts of things, they have very high clearances, and you think about that in terms of choosing medications for the length of a case or that sort of thing. And we also have to think about if we have a patient whose kidneys are not functioning, then filtering function will be lower than normal, and that patient perhaps will not need the same dose of drugs. So lots of renal pathophysiology is important for the practice of anesthesia and for thinking about human health. So on the screen here, I have a number of indicators that can say something about kidney function. So the first thing here is plasma urea, also called BUN, blood urea nitrogen. So plasma urea should be around 6 millimolar or 10 to 20 milligrams percent. If the kidneys are not filtering appropriately, then you would expect plasma urea to increase with dysfunction. Now, there are other reasons why plasma urea could increase. Maybe a person's got a bleeding ulcer and they're breaking down the blood and the protein is going back into the blood, and that's increasing urea. So just because someone had an elevated urea doesn't mean they have kidney dysfunction. Maybe they have a bleeding ulcer. Maybe they're taking steroids for inflammation, and those steroids are breaking down peripheral proteins. So you'd have to rule some other things out, but can be an indicator of how the kidneys are working. Plasma creatinine. So I want to call your attention to the idea that plasma creatinine is a byproduct of muscle metabolism, and a lot of times we're assuming plasma creatinine is fairly constant. Remember, creatinine is freely filtered, slightly secreted, not reabsorbed, and therefore the clearance of creatinine, pardon me, is a measure of the glomerular filtration rate. So we'd expect a creatinine clearance to be between, say, depending on your gender, say 90 and 140 or something like that. Plasma creatinine, remember, we sometimes can memorize that plasma creatinine should be 1 milligram percent, 1 milligram per deciliter, but there's a range there. Remember, Mrs. Goldberg in the nursing home should have a plasma creatinine that's maybe 0.6 or 0.7. You have somebody with a big muscle mass who's doing a lot of activity, then maybe their plasma creatinine is 1.5. So we memorize that 1 milligram percent is the typical creatinine, but remember there's a variation there, and we're really going to have to take into consideration somebody's age, somebody's gender, somebody's muscle mass when we look at that number. Bottom line is, if you know what the kidney function is, and you know that plasma creatinine production is fairly constant, then increases in plasma creatinine then can serve as a marker, of sort of a biomarker of renal function. If your kidneys are not filtering the way you would expect them to, then you would expect plasma creatinine to go up. All right, plasma potassium concentration. Now you remember what plasma potassium concentration should be? Should be about 4 millimolar. Maybe we'd say a range of 3.5 to 4.5, something like that. We're very concerned about hyperkalemia and kidney dysfunction because remember, your kidneys secrete potassium in the distal nephron, and if that process is impaired, plasma potassium will rise. That can be dangerous for resting membrane potentials, particularly for that in the heart. Plasma osmolarity. Plasma osmolarity should be 295 to 300 milliosmolar. And if you are unable to regulate the concentration of your urine, you might expect changes in plasma osmolarity. You might expect for plasma osmolarity to go up because you'd be losing fluid in the urine, a normal range of urine concentration. We can get our urine as concentrated as 1400 milliosmolar. Your plasma concentration, it could be, 40, 50, 60, something like that. If we have a decrease in the urine density, something called urine-specific gravity, we're losing too much water in the urine. So late stages of kidney dysfunction, you'd expect people to not be able to make urine. Early in kidney dysfunction, people are actually making a fair amount of urine. They're not able to concentrate the urine. They're losing sodium in the urine. Something I've heard a clinician call dumping sodium, and people might not be able to make it through the night without going to the bathroom when their kidneys are dysfunctioning. So this is a particular instance where you have to think about, is this early dysfunction or later on in dysfunction? Finally, we can talk about pH. Your kidney's job is to filter the plasma and secrete hydrogen ion. If your kidneys are not able to get rid of acid, that acid is going to build up in the blood. And then that's going to interfere with your ability to regulate the pH, and your plasma pH should go down, and that would be acidosis. So we've talked about the GFR as a measure of kidney function. GFR, we throw the ballpark out that about 120 mils per minute is your typical GFR. If your GFR is below 60, you may be maintaining homeostasis, but you have no reserve. So you've lost renal reserve. If you're, oh, you know what, let me start over. If your creatinine clearance, or your GFR, is between 60 and, let's say, 100, and sometimes that's what your lab reports give you, your GFR is between 60 and 100, which is not as helpful as actually knowing what the GFR is, then you've lost reserve. So you have no reserve. If your GFR is below 60, then you have renal dysfunction. You are losing, because 60, what's magic about 60? That's really the minimum your GFR can be, and you maintain homeostasis. When your GFR is below 60, you're starting to, you not only lost your reserve, you're losing major physiologic function. So that's called renal insufficiency. If your GFR is less than 25, then you're in definitely in renal failure and end-stage renal failure. And then if your GFR is less than 10, then you're going to have a condition called uremia. Now, uremia is elevated BUN. If we're talking about nitrogenous wastes in general, there's another term, azotemia. So that's all your nitrogenous wastes. Uremia specifically refers to urea. And the thing is, when you have a buildup of urea and nitrogen wastes in your body, it causes all kinds of problems. You're going to have nausea, your gut isn't going to work, you will be more insulin resistant, which is kind of weird because maybe you were insulin resistance is what put you down this path in the first place. So that's sort of an overview of stuff that's happening when your kidneys are going bad. Now, there are genetic conditions. These are fairly rare, but think about how mutations surrounding kidney function could cause problems. So, renal glucoseuria. I made the comment the other day about don't look for zebras when you say hoof prints, and you all gave me a funny look. This is exactly the situation. So, most of the time when somebody has glucose in their urine, you would say, oh, this person has diabetes. However, there is a genetic condition called renal glucoseuria, and it's because that SGLT transporter has a mutation in it. So if you can't reabsorb glucose, then glucose goes in the urine, you pull fluid with it, so you pee a lot, you're pulling fluid from the body, so you feel thirsty, and you're losing a nutrient, so you feel hungry. There's also a drug, and I want to say it's Invokana, and maybe I'll look that up before we get to class, that inhibits this transporter. So then you have glucose going out in the urine. It may help people regulate their plasma glucose and may help them lose weight, but they could also have these symptoms associated with using that drug. Cysteine urea is a genetic condition in an amino acid transporter, and if you're not reabsorbing these amino acids, they're building up in the filtrate, causing a precipitate, and that can contribute to a kind of kidney stone. Bartter syndrome, I don't expect you to memorize that name, but that's the problem in the LUT transporter. That's the sodium potassium 2-chloride cotransporter. There could be other mutations involved with that. The problem is if you have a problem with potassium or chloride channels or a problem with this loop transporter, then you're not reabsorbing sodium and potassium and chloride. Those ions are going out in the urine. Those ions are not contributing to the large gradient in the medulla, and so you're going to lose salt in the urine, person will be hypokalemic, and disruptions in potassium can cause acid-base disorders, and we'll talk about that when we get to acid-base. Lydell syndrome is a problem with the sodium chloride transporter in the distal tubule. Remember that's the transport that's sensitive to thiazide diuretics. Again, if you don't have this transporter, you're going to lose salt in the urine, and this is a potassium-losing diuretic. So even though it's not directly here, indirectly it does relate to potassium and calcium. So you will lose those in the urine, and there will be acid-base problems as well. Lydell syndrome, your principal cell epithelial sodium channels. So remember, those are the cells that aldosterone works on. And so you have the ATPase on the basolateral side of the cell, and on the luminal side of the cell you have those sodium channels. If those channels are just open all the time and you got a bunch of those channels, you're going to be reabsorbing a lot more salt than you actually need. You may be losing potassium, and then that causes metabolic problems. But hopefully you can see if you're reabsorbing more sodium than you need to, you will have hypertension. Pseudo-hypoaldosteronism. So aldosterone is the hormone that works on those principal cells to help you reabsorb potassium, to reabsorb sodium and secrete potassium. If you have a condition where you're not responding to aldosterone because you have a defective receptor, then you will not be reabsorbing sodium. So you'll have salt wasting, possibly hypotension. You'll have hyperkalemia because you're not getting rid of potassium, and the potassium then has an effect on pH, which we will talk about at a later time. If you have high acidosis in the distal tubule, now you have what's called an alpha intercalated cell. Alpha intercalated cells have a hydrogen ATPase, and then you reabsorb bicarbonate on the basolateral side by bicarb chloride exchanger. So if there are mutations in either of these proteins, then you'll have an impairment in your ability to secrete acid. When acid builds up in your blood, it dissolves the bone, and so osteomalacia can be a side effect of a metabolic acidosis.